The 2018 David Halliday and Robert Resnick Award for Excellence in Undergraduate Physics Teaching goes to Dr. Bradley Ambrose of Grand Valley State University. So Dr. Ambrose earned his BS in physics at Yale and his MS and PhD both from the University of Washington. Since 2013, he has served as professor of physics at Grand Valley State in Allendale, Michigan. During his time at GVSU, Dr. Ambrose has taught a variety of courses. The courses for teachers have long been taught in an inquiry-based style, but he has incorporated inquiry-based components into all his other courses as well. His approach is student-centered, actively engaging the students in learning process and empowering students to take the next step on their own. He is a master at asking questions to stimulate student learning, helping students solve problems themselves rather than just telling them the answers. Students and colleagues alike rate his teaching as excellent, as evidenced by his being selected as one of several campus-wide teaching awards in 2006, as well as GVSU's Outstanding Teacher Award in 2014. In addition, he has served as president and section rep for Michigan State, the Michigan section of AAPT. It is for these achievements and the other wonderful things he has done for physics education that we are proud to present the Halliday and Resnick Award for Excellence in Undergraduate Physics Teaching to Dr. Bradley Ambrose.
Thank you very much, George, and thank you all for coming. And please let me know if I have just a few minutes left. I feel like I might go over because I have a lot that I would love to share, especially a lot of gratitude. I'm sure this room is filled with many people from whom I have learned much. And I apologize if I don't get to name you in person by name by the time I'm done, but you probably know who you are. But I do want to recognize so many friends and colleagues of mine in physics education, in physics education research. Also those who nominated me, Richard Valerie and Karen Gibson, and Karen is here. I'm so glad she's here. I'm also glad my better half, Alice, is here. She's a newbie. Please treat her and welcome her to this, her first AAPT meeting. I also want to share with you we have so much in common because we are part of AAPT. What we have here in common is we love to teach physics. But my talk is entitled, We Teach More Than Physics. So let me get what we teach out of the way by saying, when you come to my office at Grand Valley, you'll see this quote on my door, and Karen can attest it's been on my door since day one, since I started in '99, that this is what I think of and hope my students think of as physics. Nature is an endless combination and repetition of a very few laws. She hums the old well-known air through innumerable variations. Rather than list Newton's laws and E&M and everything else that we love to teach, that's why I hope my students come away with when they're finished with my course or courses. But of course, we teach more than just the content, and what we also aim to teach, I can't also make an exhaustive list, but I think you'll agree with the things that I've listed here as examples, and I won't read them all. But we like to think we help our students break problems that are massive or seem massive and break them into smaller, more manageable pieces. We hope we get our students to communicate more effectively with each other as students, as future citizens, about scientific principles, scientific concepts, the nature of science. We hope that we get them to learn how to learn more effectively. I think we might agree with those things, and I'm sure there are more we might put on that list. But I think there are also things that we teach, whether we realize it or not. And I think Frank did a really good job of expressing some of these things and how being more social media active in a proactive way can ameliorate some of these things. But we teach sometimes, whether we want to or not, whether or not physics is something that our students feel they're capable of doing. And I think most of us here in this room would answer to the affirmative. Yes, we want our students to think that, yes, physics is something I know my students think. Physics is something they can do. But this is something that we teach whether we realize it, whether we attend to that or not. We also teach, and our students learn, whether we realize it or not, whether they think physics is something that's worth their time, their finite energy doing. And even if they do think that, sometimes our students learn positively or negatively whether or not they belong to the community of physics doers, whoever they think that community might be. So we hope that, at least I hope, that as I continue to teach, and that's what our mission is here, to broaden and make more inclusive the accessibility for students to not just realize they can do physics, not just it's worth something doing, but it is a community to which they can belong should they choose to. And a lot of what I do in my teaching is informed and strengthened and tested by what we have learned from physics education research, my line of research. And if you saw me give talks when I started in my career, when I described to my audience what physics education research is like, I would usually start with a graphic like this. And in years hence, it has grown. So not just investigating student learning and testing ideas for more innovative teaching and seeing the effect of that teaching, but developing models of actual student thinking and student reasoning, which has been really exciting to see happen and even get involved with. And I would dare say in the past few years, this link is getting stronger. That we're actually making connections between the nature of student thinking and reasoning, whether they're thinking by intuition or whether they're thinking by more robust conceptual reasoning structures, and how that can be detected in our instruments, those instruments being written questions and interviews and such. I think we're getting a more stronger handle on what we really mean by improving student learning and student understanding by what we try to do. And for those of you who are not in physics education research, I think you would agree that to be a uniquely effective teacher, we are always learners. We're always attentive learners to our students, to our future students. For teachers who are just in the preparatory stages, they learn content knowledge, they learn pedagogical knowledge, and if they are lucky enough to be participating in an innovative teacher preparation program, then they also learn about pedagogical content knowledge in their field or in their fields of future study, where they start to learn about the education research literature in their field. And this idea that is named pedagogical content knowledge, thanks to Lee Shulman back in 1987, and since then lifted up by many, many other educators and education researchers. I've stolen this figure from Eugenia Etkina, and I've used it N+1 times. I can't tell you how many times, including this past summer when I got to teach in Germany for future teachers in many different areas, getting them to see how education research literature can be helpful for them even as they get started in their teaching career, and certainly as they go on in their teaching career, to help them learn about their students and to help them think about where their students are and to guide their thinking and to make their teaching more effective. And certainly PER, the results of PER have and continue to be an important source of PCK, and that's a lot of what we do. To take this a little step further, to say that teachers who are uniquely effective are also always learning, at the process of learning. I can tell you personally, this past summer, as I said, had the privilege to teach in Germany for a few months, and no, I did not teach in German. I took German. You don't want to hear me speak German. I can go to a bar, I can tell you what beer I want to order effectively and how many, but I don't think I'm much more functional in German. I'm hoping to take more German this coming year. But to put oneself in the position of a learner, I actually took introductory German while I was teaching. And it was a unique experience to be in the vulnerable position of being a novice. And that can be really interesting and really useful and a refreshing reminder for teachers of what it's like to be a beginner. I want to share one other example of that kind of thing with you. And if you'll indulge me for about 90 seconds or so. This is me taking a test as a student. Not many of you know I'm taking ballroom lessons, and this is actually about my 10th year taking ballroom dance lessons. And this is a test. I did not want to show you or try to brag about how good a dancer I am, because if I did, I'd show you how I would do a memorized, choreographed routine. This is not memorized. This is all lead and follow that I'm doing with several of my instructors. And their job is to see how well I'm communicating with them. They get to sense my lead. They see how well clear it is, how easy it is to respond to my lead. And you notice I'm teaching, if you're a dancer, you probably notice I'm teaching dancing several of the same patterns, just not quite all in the same order, which is probably a good thing. But sitting off camera is a professional adjudicator who's also taking careful notes. And this is a test because it's an assessment, and I would say it's both summative and formative. Summative in the sense that this is actually the formal conclusion of my, my first year of college level ballroom. I've already learned my high school diploma of ballroom a couple years ago. So this is the formal ending of that. I see this and I see so many of my mistakes. So thank you. I'm trying on purpose to talk to you and not watch the video. But what's I think useful and what struck me as I look back on this was this assessment, if you want to call it this, and it is summative but both formative because of the comments that I got from the professional adjudicator who gave me kudos for things and pointers for future lessons. Turns out many months or many weeks of future lessons. With a really strong emphasis on how well was I communicating with my partner, how strong, how effective was my connection with my partner. So I thought about this even more, and I thought, as a teacher, going back to my comfort zone, the physics classroom, as a teacher, I think I'm effective, most effective, I thrive best when I have, we call it formative assessment, but I could call it, or I would fancy the idea of calling it developing a really strong connection with my students in many ways. I don't teach by lecturing, as many of you are familiar with physics by inquiry and other innovative teacher, more student-centered formats of teaching. It's much more the students are in control, the students work collaboratively, the role of the instructor is to teach by questioning. And that is what I do. I give continual feedback as I connect with my students about what they are always struggling with, how I might be able to guide their thinking as I work with them day by day, minute by minute. I get moment by moment sometimes feedback, which can be really helpful as I figure out what is going to be helpful to guide their thinking, what may not be helpful to guide their thinking, whether I'm doing anything by the guidance I think I'm giving, how their thinking is evolving, and even how the confidence that they feel about their thinking is evolving. And as some of you probably would recognize, yes, that's a physics by inquiry textbook sitting on the table in front of me as I talk with this group of Grand Valley students. And I feel that when I am at my best connecting and engaging with my students, I feel like I'm connecting and engaging with them at a level that's almost like this. And thanks to physics education research, you don't have to have just one-on-one teaching, like some analogy that I would want or could try to make with teaching and dancing, try to work out. It doesn't work out, I'm not going to try. But to make that connection kind of work with the resources that we have, physics education research has illuminated many ways for us to operate as teachers. And I want to give a quick example from work I've done, and I don't know if he's here. Michael Whitman is a co-PI, has been a co-PI for me in this project called Intermediate Mechanics Tutorials. Modeled after proven research-tested, research-based, inquiry-based teaching by questioning materials developed at the University of Washington, where I got my PhD with Lillian, who is also here. I'm so glad she is here. And also that Michael was born and raised with at his PhD institution of University of Maryland, working with Joe Reddish. We worked with a model that worked before for us, but with this new population, this new level of upper division students. So I'm going to give you a quick example of what I see now looking at this as making a connection, developing as formative feedback can help us and make connections and be in tune with where our students are. You're probably familiar with the sequence. We first look at how students tend to believe or what they understand about a topic before we roll up our sleeves or before we do anything special in the class. I'm going to give an example about harmonic oscillations in 2 dimensions, just because that's one of my favorite topics when I teach this course. And for those of you who maybe not teach this, but who teach 2-dimensional motion, you know 2-dimensional motion is not just twice as difficult as 1-dimensional motion. It's more than twice as difficult. Same when you get into the context of harmonic oscillation. So one question that I often give my students before we really get down to brass tacks and think of conceptual underpinnings is to give them a chance to look at some trajectories of 2D oscillations from the textbook and to ask them, for each one of these, is it possible for a 2-dimensional oscillator to follow this trajectory? And if so, compare for me the frequencies along the x and y axes. Is omega 1 greater than, less than, or equal to omega 2? And explain your reasoning. And if not, explain why this couldn't happen. Originally, this question was phrased in terms of a comparison, asking for a comparison of spring constants or force constants in the x and y directions. And I changed it to make it perhaps a little easier looking at frequencies. So as you've been looking at this, maybe you've been thinking about what the correct answer is. I'll save you any more toil. I'll tell you, for the first 2 cases, there's 1 cycle of motion along the x direction for every 1 cycle in the y direction. So the frequencies are the same. In case 3, they are different. In case 3, the x oscillations happen more frequently, twice as frequently as they do in the y direction. So omega 1 is bigger than omega 2 in that case, twice as big. This was a difficult question, as some questions like this tend to be. And the question elicited most often a kind of intuitive reasoning that students thought would apply either to whether they were being asked about the force constants or about the frequencies. They tended to look at the shape of the path, and in particular for a situation like case 2, they tended to treat if the oscillator is going farther in one direction than in another, then there must be a difference in the force constants. K1 is less than K2, as one student said, because the spring goes farther in that x direction, so the spring must be less stiff in that direction. Or similarly, when asked about omegas, they said a similar sort of answer. We have an oval curve with the x-axis longer. Now, if this does seem to you rather intuitive reasoning, I would agree. And this is helpful for us to know. So here's one type of connection, one piece of vital feedback that I as an instructor need, that if students are going to use intuitive kind of reasoning to answer a question like this, then I have to address it as an intuition that probably needs refined. And so the tutorial, the collaborative teaching by questioning activity that goes with this helps students go through the steps one by one of recognizing what factors affect the frequency, how a trajectory like this can help you determine relative frequencies, and why it's things like the spring constant that would affect the frequencies and not the size of the perturbations or displacements from the origin in the x or y direction. And this tutorial is one of many, and again, modeled after a model that's been successful, based on checkpoints where students call the instructor over, they have a conversation that's often very important to make sure that they are on the right track, and that is formative assessment in both ways, and vital for the success of the tutorial and the learning goals of that tutorial. And something that I found useful for this particular topic was that there was the necessary cycling back that helped with the intuition getting further refined here in the case of the homework. If students were going to attach some sort of meaning to the relative amplitudes, then let's do that. Otherwise, if they still want to focus on that aspect, they still may revert back to their old way of thinking. And indeed, for those of you who are familiar with refining intuitions along the lines of David Hammer and Andrew Elby, this is exactly what this question is intended to do. I just didn't realize that until after I had written it. And indeed, this kind of cycling back and the fact that there is a homework that students they turn in, and very often I give them the chance to revise it and refresh their responses if they still need another look. That's also then formative assessment, another step of the conversation. And that particular homework I found to be rather helpful because on exams that are more summative in their assessment, looking at how well students can interpret diagrams of these XY trajectories, both qualitatively, just like on the ungraded quiz or the pretest, or quantitatively when I ask for ratios of the force constants. The students tend to do not just better, which was shown from the original version of the homework or original version of the tutorial without the revised homework, but then with several classes in which there was the implementation of the revised homework, a significant jump in the performance of the students. So I think this is a successful case of refining intuitions. And again, if you are a teacher who likes to operate in the sense of, well, I just heard an incorrect answer from my student, but that's probably a correct answer to a different question. What's that question? If you don't know about Andrew Elby's work and David Hammer's work in this, it goes way back to 2001. Read it. You'll resonate really well with it. So to start to wrap up, I think we do teach more than physics. And when we look at and have communication, we have conversations with students in class. And thanks to work like Frank is doing, which compared to mine makes my work look hopelessly low tech. But that's what some of the classroom conversations are going to be like. And when we have the chance, informed by what PER can tell us and informed by what solid teaching, innovative practices there are out there, we cannot just teach physics. I think we can teach more than physics. We can help our students engage with other ideas, with differing ideas from their own, and do so objectively. These couple of first sub-bullets are what I tell my honors, non-science major students who are about to delve into a properties of matter lab, and then for the rest of the semester, guiding or physics by inquiry is what they do. I insist that they think about listening and responding to each other's ideas just as they would want themselves to be listened and responded to. And don't worry about who's right or who's wrong. Worry about what's right and why. And I like to think that my students are becoming more reflective thinkers about their own thinking, about their own progression of thinking, and I would like to think they not only take more responsibility for their learning, but I would hope they also trust and gain confidence in their thinking by being more reflective, by having the chance to have these conversations. And I think I do that, and sometimes I even get evidence that I think that I do that. One of my favorite conversations with students went like this. A student just knocked on my office door soon after an exam, and she told me this: when I got stuck on a hard problem during that exam, I heard your voice in my head asking me questions just like you do in tutorial. I could have just dropped the mic right then and there. This was even before I got tenure. I could have just left. I was so happy. And I had a chance to do a sabbatical at Seattle Pacific University, where I was reminded of some favorite readings of mine, even as a college student. One of them actually resonated quite well with what I was hearing from this student. If you forgive the predominantly masculine pronouns you see here, this was written quite some time ago. But what this student told me could not be a pure example of what a wise teacher leading you to the threshold of your own mind would be. And boy, wouldn't I like more of my students to do that. I hear Lillian's voice when I read much of the rest of the quote. A teacher can never do the thinking of their own students, nor can an astronomer, nor can someone who's well-versed in the science of numbers. So with gratitude for what I've learned and what I will continue to be learning from many of you in this room, I hope that we will be teaching physics, but also teaching more than physics, teaching confidence, teaching that our students belong, that retention in STEM, even retention in college, is improved by having these conversations with students that might happen in the classroom in an ordinary way, but it can have more than ordinary outcomes. I would love to have conversations like this one with a student. But even better, I would love to have conversations like this with a student where it's not my voice that she hears, but her voice asking those questions. So again, in gratitude, I want to thank the American Association of Physics Teachers for considering and choosing me for this award, and for many of the people you see listed here who I have learned from and will no doubt continue to learn from. And again, apologize if I have not mentioned you yet by name. Be assured I am most grateful. So thank you.
I think we have time for a few questions for Dr. Ambrose, so anyone out there? Oh, I'm sorry. I can't. You see? The light.
I couldn't hear the last part of your question. I still test sophistication. Thank you. Yeah.
How do you separate the refinement of intuition, which is how you phrased it, from test sophistication? Because to me it seemed like they went hand in hand, but you seem pretty convinced it's one rather than the other. Or am I overreading that?
I'm still not sure what you mean by test sophistication.
Being familiar with the type of question that's being asked because you were getting more and more examples of it, for example.
My students have lots and lots and lots of practice answering questions in low stakes arenas like an ungraded quiz and high stakes arenas like an exam. They get practice answering those questions, but I think the practice that they get with the ideas underlying what I showed here, two-dimensional oscillations, is what's happening by virtue of them not getting the same question over and over again, but because of the things that I'm directing them to, guiding their thinking toward when I have the chance to work with them one-on-one, when they get the chance to work with their peers. Does that answer your question?
I think we have time for one more. Okay,
Well,
thank Dr. Ambrose again, please.
thank you very much.
We have one more presentation to make here, one more award, and that is for Tiffany Taylor. Is Ms. Taylor here? Thank you.